Hello everybody. In this video, we're going to talk about multivariable functions. Now previously, we've studied different kinds of functions. Right? In past courses, you've probably learned about functions from the real numbers to the real numbers, a single number input, a single number output. And in the last two videos, we talked about vector functions. Those are functions which have a single input, a parameter that we often think of as t for time, and the output is a vector, and typically a vector with two components or three components. Starting in this video, we're going to shift our focus to multivariable functions. So using our notation, we would write this as f goes from R2 to R. In other words, two inputs and one output. Now, this is different than the kinds of functions we have before, two inputs instead of two or three outputs. Right, we'll often write these functions as f of x comma y equals z. But in case you're wondering why this kind of function is called a multivariable function and the other is not, that's because of the inputs. In this case, these functions, you'll see multiple variables, x and y. But in the vector functions f of t, even though there's multiple components, there's really only one variable, the single variable t. All right, so here's some examples of some multivariable functions. And we have z equals 3x squared minus 4xy plus 7y cubed. We have z equals x times cosine y minus 5 times y. We have z equals the square root of x squared plus y squared. And z equals 1/4 times a quantity 2x plus 3y plus 5. And interestingly, this last equation can be rearranged to give you the equation of a plane, which we'll say more about later. But these are all examples of multivariable functions. Graphing multivariable functions is really hard. Right? So first, let's talk about the axes. In ordinary functions, right, y equals f of x, right, we'll draw an xy axis. Right, x is the horizontal. Those are your input values. For each value of x, you plug it into your function, and you get an output of y, and that gives you the height on your function. For multivariable functions, right, we have three dimensions, x, y, and z, and we'll draw them like so. And this might be kind of hard to visualize, but the x, y, and z axes, they're all perpendicular. The way I like to think about this or visualize it is imagine these axes as the back edges of a cube. And so here we have a cube in purple. And think of it as a slightly transparent cube, so you can kind of see these back edges with these dashed lines. These back edges would align with the x and the y and the z axes. And so going back down here, the inputs of this function consist of all these points here in the plane. Right? So these are the x and y values. And this is kind of the horizontal component of the function. It's traditional, whether you have a two-dimensional or a three-dimensional environment, right? The input values are arranged horizontally, and that's why the z-axis points up. And in general, we won't do a lot of graphing of points because points are extremely difficult to visualize unless you have some kind of guidelines or markers in coordinates. So for example, if we draw x, y, z and a point P, right, just by looking at this graph, it's hard to tell where it should be situated in three-dimensional space. Unlike an xy axis where there is no ambiguity, that third dimension makes it more difficult to interpret. Right, we could draw some lines to show where this point is positioned. So here, the point is 4 units along the x-axis. I'll draw a dashed line going across. 3 units along the y-axis. I'll draw another dashed line. And this very light gray point down here. And it's kind of like, think of that as the shadow this point would cast if a light was shining down above it. Then from this point in xy, we would go up by 5 units in this picture. So this would correspond to the point 4, 3, 5. But in general, we're not going to be graphing points very much. It will help to graph functions sometimes. The simplest function to graph, we've seen pictures of these before, function z equals ax plus by plus d. Right? A function with this general form could be rearranged in this form, which we know is the equation of a plane. In this case, the normal vector to this plane, the vector which is perpendicular, as always, is the coefficients of x, y, and z, which are a, b, and -1. And so this we can kind of visualize as a flat plane. We can try to visualize more complex three-dimensional graphs by calculating what are called cross-sections, which are, I think of those as two-dimensional graphs that are stacked along an axis. So for example, let's say you want to determine the shape of the function z equals x squared plus y squared. You could try different values of z. Right? So here I'm considering the value z equals 4, 3, 2, 1, 0, and -1, and try to understand, when we plug these values in for z, what are these graphs of? In this case, I chose this example because it's easy to see that these are the equations of circles with a radius which is getting smaller and smaller. When z equals 0, x squared plus y squared equals 0, that just corresponds to a single point, 0, 0. And any negative values of z, well, there are no solutions, which in this case means there's no points on this surface which have negative z coordinates. And here, in the same corresponding colors, I've drawn graphs of circles which are getting smaller and smaller as they move down. Right, so we start to get an idea of what this looks like, but there are multiple 3D shapes which are created from stacked circles. So for example, a cone is also created from a stack of circles that get smaller and smaller. So we might need to look at other cross sections. In other words, pick a different value for one of these variables. In this case, what if we let x equal 0? And if x equals 0, we're left with z equals y squared, which we know is the graph of a parabola. So here, when x equals 0, that means this should be aligned with the yz plane. Right? We have a parabola right here. So these circles should fit within this parabola. And if you want, you could also look at cross sections when x equals 1 and x equals 2. In that case, it's like we're taking slices of this shape which are closer and closer to us, the viewer, along the x-axis. In which case, these would actually look like parabolas which are raised a little bit higher, and it's kind of hard to visualize. Right? But if we took another cross-section closer, we might get a parabola, right, which stops at this light blue circle, for example. Right, so there's lots of different ways to visualize this. There are, of course, applications online which you can take a look at to graph 3D curves. But in general, or 3D surfaces, I should say. But in general, we won't be really concerned with graphing them. I will show you a couple of examples, but I'm not going to expect you to produce these on your own. It just helps to have an understanding of the nature of 3D surfaces so we can interpret the algebra and the calculus and the derivatives we're eventually going to calculate. This is a really interesting graph. Z equals 1 minus x squared. And I am thinking of this as a function of x and y. But you'll notice there's no y here. And so imagine what happens if we try to take cross sections along the y-axis. In other words, right, set y to different values. Y equals 0, y equals 1, y equals 2, y equals 3. In each case, right, plugging in y has no effect. we're left with the same equation here, which means that these cross sections, each one of these is a parabola facing downwards because of the negative sign in front of x squared. Right? And its vertex is at z equals -1. So each cross section, when y equals 0, when y equals 1, when y equals 2, when y equals 3. Right? Those cross sections line up along the y-axis. It kind of looks like a tunnel if you were, say, you're positioned here and looking straight down along the y-axis. Right? This is what you would see. In this case, again, if you're positioned right here, the x-axis will now look like it's going to the left. The z-axis still points up, whereas the y-axis, well, it's pointing directly at you, the viewer. And here's z equals 1 minus x squared. All these cross sections line up, so it would look as if you're going down a tunnel in this case. Now, there's many other functions which exist, but we're not going to study them all here in this class. There are other math classes you can take where you will study these other kinds of functions. We'll basically limit ourselves to these 4 different types of functions, right? In fact, we don't really even talk that much about functions from R to R, right? Those represent curves in the plane, which you've probably studied in another class. We did talk about vector-valued functions a lot, functions from R to R2 and from R to R3. We have these forms right here, and they're tracing out curves on the plane or curves in 3-dimensional space. As we've seen in this lesson, the functions f of xy equals z, that represents a very special kind of a surface in space. Right? We saw they could represent something like a tunnel, represent something like this shape, which is called a paraboloid, by the way, represent lots of different things. There are other functions. We did kind of talk about functions from R2 to R2 and R3 to R3, those functions which involved multiplying by a matrix. But more general functions involving operations like squaring or cubing or square roots or trigonometry, right? Those more general functions, you can think of them as associating to each point associating a vector. Right? So for each point in a plane, associate a vector. For each point in 3-dimensional space, associate a vector. These are sometimes called vector fields, and they're used to model things like airflow or fluid flow. It's really interesting. You'll study these a little bit if you took a course called Calculus 3, which is more focused on just pure calculus. You would also encounter these if you were to study differential equations as well. You could consider a function from R3 to R1. This is a function which it would be really hard to graph. Right? We couldn't graph that the same way we graph f of x equals y or f of xy equals z. Right? These functions would have the form f of xyz equals w, but that's 4 coordinates, so we can't really draw a picture of it. Right? This function represents taking a point and associating a single value. The main example I like to think of for this kind of function is, let's say you have some kind of a 3-dimensional space or room. You're associating some quantity to each space. So this would be good for modeling, say, heat or temperature at each point. And if you were to model a kitchen and the stove is on, the points which are closer to the stove, which would have a much higher heat value than, say, those points near a window if it was cold outside. Right? And you can analyze functions like this to understand things like the flow or change of heat as it disperses through a room. 2 other kinds of functions which you could encounter in other courses. F from R2 to R3. Right? We actually did see one of these as well. There's one way you can think of the equation of a plane. Right? We often write it as ax plus by plus cz equals d, but there is kind of a vector version of the equation of a plane, which has a form more like this. But in general, if instead, right, you have three components and each one of these are general functions, which again could include exponents or trigonometric functions, this describes a general surface in space. Kind of like functions from R2 to R, but a more general class. Just like when we study functions f of x equals y. You can graph curves like parabolas, but you can't graph something like the trefoil knot curve. Right? You need this more general form to capture different types of curves which would not pass the vertical line test. Similarly, these functions f of xy equals z, those can be used to graph a surface in space that passes a vertical line test. Right? For each xy value, you can only have one corresponding z value. But functions of this form, from R2 to R3, they can be used to specify any general surface in space. Things like spheres and ellipsoids, or anything you can imagine, can be specified with a function in this form. And finally, functions which take 3 inputs and give you 2 outputs. One of the most common uses of a function like this is to take the points in a 3-dimensional space and compress it onto a flat 2-dimensional surface. And you'll see that a lot in actually computer graphics, which is concerned with how you take a 3-dimensional scene and render it to your screen. Right? So if you were to take an advanced course in computer graphics, which because of the math is also one of my favorite courses to teach, you'll actually see a lot of functions of these two kinds as well. And so many kinds of functions exist, but not all of them are studied here. And so the purpose of this video was really just to give you an introduction and a feeling for what functions, multivariable functions, are like. So we haven't really done a lot of math in this video. For the exercise for this video, why don't you try drawing something in 3 dimensions? See if you can copy this graph of a paraboloid. Doesn't have to be a colorful graph, but it's nice to get used to drawing 3-dimensional shapes. It's kind of fun. So we'll call that the exercise for this video. That's probably a good stopping point for this. In the next video, we'll start calculating derivatives for these kinds of multivariable functions. That'll be next time. Thanks for watching.